In computing, an interface is a shared boundary across which two or more separate components of a computer system exchange information. The exchange can be between software, computer hardware, peripheral devices, humans, and combinations of these. Some computer hardware devices, such as a touch screen, can both send and receive data through the interface, while others such as a mouse or microphone may only provide an interface to send data to a given system. Hardware interfaces exist in many components, such as the various buses, storage devices, other I/O devices, etc. A hardware interface is described by the mechanical, electrical, and logical signals at the interface and the protocol for sequencing them, sometimes called signaling. A standard interface, such as SCSI, decouples the design and introduction of computing hardware, such as I/O devices, from the design and introduction of other components of a computing system, thereby allowing users and manufacturers great flexibility in the implementation of computing systems. Hardware interfaces can be parallel, with several electrical connections carrying parts of the data simultaneously, or serial, where data are sent one bit at a time. A software interface may refer to a wide range of different types of interfaces at different levels. For example, an operating system may interface with pieces of hardware. Applications or programs running on the operating system may need to interact via data streams, filters, and pipelines. In object-oriented programs, objects within an application may need to interact via methods. In practice, a key principle of design is to prohibit access to all resources by default, allowing access only through well-defined entry points, i.e., interfaces. Software interfaces provide access to computer resources, such as memory, CPU, storage, etc., of the underlying computer system. Direct access, i.e., not through well-designed interfaces, to such resources by software can have major ramifications, sometimes disastrous ones, for functionality and stability. Interfaces between software components can provide constants, data types, types of procedures, exception specifications, and method signatures. Sometimes, public variables are also defined as part of an interface. The interface of a software module A is deliberately defined separately from the implementation of that module. The latter contains the actual code of the procedures and methods described in the interface, as well as other private variables, procedures, etc. Another software module B, for example the client to A, that interacts with A is forced to do so only through the published interface. One practical advantage of this arrangement is that replacing the implementation of A with another implementation of the same interface should not cause B to fail. How A internally meets the requirements of the interface is not relevant to B, which is only concerned with the specifications of the interface. See also Liskov substitution principle. In some object-oriented languages, especially those without full multiple inheritance, the term interface is used to define an abstract type that acts as an abstraction of a class. It contains no data, but defines behaviors as method signatures. A class having code and data for all the methods corresponding to that interface and declaring so is said to implement that interface. Furthermore, even in single inheritance languages, one can implement multiple interfaces, and hence can be of different types at the same time. An interface is thus a type definition, anywhere an object can be exchanged. For example, in a function or method call, the type of the object to be exchanged can be defined in terms of one of its implemented interfaces or base classes rather than specifying the specific class. This approach means that any class that implements that interface can be used. For example, a dummy implementation may be used to allow development to progress before the final implementation is available. In another case, a fake or mock implementation may be substituted during testing. Such stub implementations are replaced by real code later in the development process. Usually, a method defined in an interface contains no code and thus cannot itself be called. It must be implemented by non-abstract code to be run when it is invoked. An interface called stack might define two methods, push and pop. It can be implemented in different ways, for example, fast stack and generic stack, the first being fast, working with a data structure of fixed size, and the second using a data structure that can be resized, but at the cost of somewhat lower speed. Though interfaces can contain many methods, they may contain only one or even none at all. For example, the Java language defines the interface readable that has the single read method. Various implementations are used for different purposes, including buffered reader, file reader, input stream reader, piped reader, and string reader. Marker interfaces like serializable contain no methods at all and serve to provide runtime information to generic processing using reflection. The use of interfaces allows for a programming style called programming to the interface. The idea behind this approach is to base programming logic on the interfaces of the objects used, rather than on internal implementation details. Programming to the interface reduces dependency on implementation specifics and makes code more reusable. Pushing this idea to the extreme, inversion of control leaves the context to inject the code with the specific implementations of the interface that will be used to perform the work. A user interface is a point of interaction between a computer and humans. It includes any number of modalities of interaction, such as graphics, sound, position, movement, etc., where data is transferred between the user and the computer system. In the industrial design field of human-computer interaction, a user interface, UI, is the space where interactions between humans and machines occur. The goal of this interaction is to allow effective operation and control of the machine from the human end, while the machine simultaneously feeds back information that aids the operator's decision-making process. Examples of this broad concept of user interfaces include the interactive aspects of computer operating systems, hand tools, heavy machinery operator controls and process controls. The design considerations applicable when creating user interfaces are related to, or involve such disciplines as, ergonomics and psychology. Generally, the goal of user interface design is to produce a user interface that makes it easy, efficient, and enjoyable, user-friendly, to operate a machine in the way which produces the desired result, i.e. maximum usability. This generally means that the operator needs to provide minimal input to achieve the desired output, and also that the machine minimizes undesired outputs to the user. User interfaces are composed of one or more layers, including a human-machine interface, HMI, that typically interfaces machines with physical input hardware, such as keyboards, mice, or game pads, and output hardware, such as computer monitors, speakers, and printers. A device that implements an HMI is called a human interface device, HID. User interfaces that dispense with the physical movement of body parts as an intermediary step between the brain and the machine use no input or output devices except electrodes alone. They are called brain-computer interfaces, keys, or brain-machine interfaces, BMIs. Other terms for human-machine interfaces are man-machine interface, MMI, and, when the machine in question is a computer, human-computer interface. Additional UI layers may interact with one or more human senses, including tactile UI, touch, visual UI, sight, auditory UI, sound, olfactory UI, smell, equilibria UI, balance, and gustatory UI, taste. Composite user interfaces, CUIS, are UIs that interact with two or more senses. The most common CUI is a graphical user interface, GUI, which is composed of a tactile UI and a visual UI capable of displaying graphics. When sound is added to a GUI, it becomes a multimedia user interface, MUI. There are three broad categories of CUI: standard, virtual and augmented. Standard CUI use standard human interface devices like keyboards, mice, and computer monitors. When the CUI blocks out the real world to create a virtual reality, the CUI is virtual and uses a virtual reality interface. When the CUI does not block out the real world and creates augmented reality, the CUI is augmented and uses an augmented reality interface. When a UI interacts with all human senses, it is called a qualia interface, named after the theory of qualia. Citation needed QE may also be classified by how many senses they interact with as either an X-sense virtual reality interface or X-sense augmented reality interface, where X is the number of senses interfaced with. For example, a smell-o-vision is a 3-sense, threes, standard QE with visual display, sound and smells. When virtual reality interfaces interface with smells and touch, it is said to be a 4-sense, fours, virtual reality interface, and when augmented reality interfaces interface with smells and touch, it is said to be a 4-sense, fours, augmented reality interface. The user interface or human-machine interface is the part of the machine that handles the human-machine interaction. Membrane switches, rubber keypads, and touch screens are examples of the physical part of the human-machine interface which we can see and touch. In complex systems, the human-machine interface is typically computerized. The term human-computer interface refers to this kind of system. In the context of computing, the term typically extends as well to the software dedicated to control the physical elements used for human-computer interaction. The engineering of human-machine interfaces is enhanced by considering ergonomics, human factors. The corresponding disciplines are human factors engineering, HFE, and usability engineering, UE, which is part of systems engineering. Tools used for incorporating human factors in the interface design are developed based on knowledge of computer science, such as computer graphics, operating systems, programming languages. Nowadays, we use the expression graphical user interface for human-machine interface on computers, as nearly all of them are now using graphics. Multimodal interfaces allow users to interact using more than one modality of user input. A user interface, UI, is the point of communication between a person and a machine. It's what you see, hear, say, and touch in order to give instructions to a device or receive information back from it. User interfaces dictate how people interact with devices and software, like mobile apps. They're designed to maximize accessibility, provide a user-friendly experience, and ultimately help drive conversions. In the past, user interfaces were basic, and consisted solely of on-screen buttons and simple menus that were controlled via a keypad, mouse, or keyboard. Today, new technologies mean UIs can be tapped, swiped, spoken to, or even gestured toward. Developments like these enable marketers and app developers to create greater experiences, capture new data points in order to better understand audiences, and analyze interactions, behaviors, and habits within apps. User interfaces are made up of many components, and they depend on the type of UI, more on UI types below, the users, and the end goal. While these factors will vary, what remains consistent is the requirement to give users the best experience. The list of elements that make up a user interface is ever evolving, particularly in the world of mobile apps, with breakthroughs and adaptations in technology, like voice recognition and artificial intelligence, AI, but here we'll cover the basics of what forms a UI. Input components, anything you use to initiate an interaction. Menu buttons, checkboxes, drop-down lists, free text fields, radio buttons, and anything you can tap or swipe. Navigational components, the elements used to move around an environment. A progress bar, breadcrumbs, and search boxes. Graphics and visuals, the components that form the basis for the UI. Windows, transitions, menus, icons, text, fonts, images, color palettes, layout, and any other signposting. Feedback, how the UI communicates back to the user. Text boxes/messages, color changes, sound prompts, virtual assistants, and haptic feedback. A variety of user interfaces exist to complement the different devices we encounter on a daily basis. Ever withdrawn money from an ATM? Was it a touch screen? Did it beep when you typed in your PIN? Did the card slot flash when it dispensed your cash? That's an example of a well-thought-out UI. Some UIs, particularly on mobile, can even be adaptable depending on how they're being used. Music apps like Spotify will switch to a stripped-back, clutter-free, big button design when connected to a car stereo to allow easier interaction. The type of user interface you're likely to have the most experience with is a graphical user interface, GUI. GUIs are found on screens like smartphones, tablets, laptops, and desktop computers. They use icons, menus, window panels, and buttons to help you control what you want to do. Depending on the device you're using, graphical user interfaces typically receive input from your keyboard, mouse, stylus, or fingers. Most desktop and laptop computers are considered to use graphical user interface components, but a growing number of brands now offer touchscreen technology, too. While it may be possible to interact with a computer via touchscreen, it's on mobile devices where this UI really performs. Touch user interfaces, TUIs, are specifically designed for interaction with touchscreen devices, but not exclusively smartphones. They need to allow clean user input while considering screen size, spacing, legibility, and accessibility. Other places you'll find touchscreen interfaces include some ATMs, in-car entertainment systems, and portable GPS devices. Though the UI on your smartphone is made up of TUI and GUI elements, it actually has its very own UI term MUI, or Mobile User Interface. Mobile User Interfaces, MUIs, have TUI components at their core, but build on them to create a dedicated UI that better considers screen size, battery life, and processing power. Think of MUIs as a subcategory of TUIs. Where you'll find graphical user interfaces on multiple devices, mobile user interfaces are found exclusively on smartphones. While MUIs must factor in accessibility, lightning-quick responses, and ever-changing screen sizes, they can make the most of the unique features they get to share living within a smartphone, like near-field communication, GPS, and biometrics to provide a more fluid user experience. Voice user interfaces, VUIs, remove the need for physical contact and let you engage with the device by speaking. VUIs have become more commonplace in recent years, thanks to advancements in natural language processing, a computer's ability to understand and respond to a human's spoken command. You'll find voice user interfaces within smartphones and smart speakers, both of which carry virtual assistants to respond to queries, like Apple's Siri, the Google Assistant, and Amazon's Alexa. Being able to interact with a device without physical touch or the need to be within view of a screen means voice user interfaces are very accessible. This makes them popular within in-car entertainment and navigation systems, as well as in smart homes, where users can speak to their devices to trigger events, like controlling thermostats or lighting. Gesture-based interfaces, GBIs, rely on movement to control and interact with the device. Using motion sensors or cameras, GBIs look for cues from physical movements, like a flicked wrist, nodding head, or moving console controller. Gesture-based interfaces are popular as they provide an intuitive way to engage with technology, making them popular interfaces in the world of gaming. Often viewed as a futuristic and advanced way to control computers and machines, the technology has been in the mainstream for a number of years, most notably alongside the introduction of the Nintendo Wii in 2006. Almost 20 years later, and with advancements in virtual and augmented reality, as well as artificial intelligence, gesture-based interfaces can offer fully immersive gaming experiences with natural movements, rather than relying on a traditional keyboard or controller for input. Whatever the device, the goal of a user interface should be the same: to not just take users from A to B, but to enable an enjoyable, accessible, and logical experience along the way. These factors are particularly critical in the world of mobile, where users can flip between apps in a heartbeat if they're not kept engaged or if they're made to jump through unnecessary hoops. Over time, mobile users develop preferences for brands, operating systems, and apps, largely dictated by their in-app experiences, sort of like brand loyalty. This is less about them completing levels, finding particular information, or winning prizes, and more about how they feel while using the app. Was it easy to access? Was the information presented logically? Did they have a positive experience in the app? Humans are creatures of habit and they warm to familiarity. It's the reason iPhone users rarely jump ship to an Android device, and vice versa. Whether you're Team Apple or Team Android, the fundamentals of a good user interface are the same. It's the execution of these principles that can improve brand loyalty, user stickiness, and customer retention. Thank you for watching this video.